45 minutes, I want to discuss the only example of a non-free theory with a one-form symmetry that we'll get to, and that already came up in several questions, which is the abelian Higgs model. And this is the theory, this is a U1 gauge theory, Maxwell theory, coupled to something, a charged, an electrically charged scalar field, phi, which will be our Higgs field, of charge QE. And in principle, QE can be any integer. We'll take it to be a non-zero integer. Maybe we'll also take it positive. Okay, very good. So the Lagrangian of this model looks very much like a mashup of the Maxwell Lagrangian and the O2 model Lagrangian, but of course there are important changes here. There's a Maxwell kinetic term for the photon. There's a kinetic term for phi, but because phi now carries electric charge, right? It's no longer a gauge invariant operator. Coupled to the photon through the usual gauge covariant derivative, and the electric charge appears there explicitly. And then there's a potential for phi, which will be of the same form as the potential in the O2 model. So it'll be a quartic potential with a mass term that could either be positive or negative. So this is a gauge theory, right? Just like Maxwell theory, A is a standard U1 connection. Phi is now charged under that, so it's a section of a bundle, and it's no longer a gauge invariant operator, unlike in the O2 model. So we are no longer entitled to study correlation functions of phi by itself. We have to work a little bit harder to make gauge invariant operators. So the thing that we're interested in the spirit of the previous lectures, is the global symmetries of this model, and in particular the higher form symmetries. And one way to phrase the question is, in the absence of the Higgs field, we just discussed Maxwell theory. We saw that it has a U1 electric and a U1 magnetic one-form symmetry. And the first thing we can ask is, which part of this symmetry survives when we add the Higgs field? Very good. So the good news is that the magnetic symmetry, which remember was a consequence of the Bianchi identity, is completely unfazed by the presence of this electrically charged Higgs field, because A is still a U1 connection, F is still dA, so dF is still 0. And that's a reflection of the fact that this model does not have any magnetic charges, dynamical magnetic charges. Phi is a dynamical field with electric charge, but there's no dynamical field that carries magnetic charge. Very good. Okay, so the electric symmetry is obviously no longer present, or at least it's no longer present in its U1 form. And the way to see that immediately is to remember that the current conservation for this electric symmetry was just the Maxwell equation. So it's what you get by varying the action with respect to A. But now the Maxwell equation has a right-hand side, which is just the electric current, or star of the electric current, right? Which is precisely the electric current associated with this phi particle. And in this case, the electric current looks something like that. Something like I, Q, E, phi bar d to the covariant B. So this is a non-zero operator. It's a non-zero gauge invariant operator, which is the electric current operator. You see it's proportional to QE because of this coefficient here, and it appears on the right-hand side of the Maxwell equation. So this used to be, or I mean, you can still think of this as the electric two-form current. The fact that it has a right-hand side, and this right-hand side cannot be written as D of some 2 form secretly that you can then use to redefine the current to be conserved. This is really a non-exact 3 form. And so the U1 symmetry is broken, explicitly broken, meaning it's absent. It's not a symmetry to begin with. Now it turns out that for general QE, a discrete subgroup of this U1 symmetry survives. This argument about the current only tells you that the continuous U1 symmetry is not there, but it's still possible, and in fact it's true, that a discrete subgroup survives, and it turns out that the thing that survives is a ZQ electric one-form symmetry. And there are different ways to see this, some more formal and some more intuitive. Let me, in the interest of time, give you the more intuitive one. So in Maxwell theory, we sort of developed the intuition that these one-form symmetries were the symmetries that prevented charged lines, Wilson lines, and 't Hooft lines from ending. So I told you to think of them as electric and magnetic flux conservation symmetries. And the reason that none of these lines could end, because there was simply no kind of operator that could have plausibly sat at such an endpoint. Let's think about what kind of operator can think at the endpoint, can live at the endpoint of a Wilson line. Imagine you have a Wilson line of charge QE living on this curve. The curve ends. What happens? Well, the Wilson line, remember the closed Wilson line is the holonomy. But if you're integrating this gauge field along an open curve with a boundary, then it's not gauge invariant because A shifts by d lambda under gauge transformations. And then this lambda evaluates at the boundary. So the Wilson line transforms like e to the I to e times lambda at the boundary point, and we call it p. So you see, it's almost gauge invariant except for a phase factor of charge QE sitting precisely at the endpoint of the line. So it transforms exactly like an electrically charged field of this charge. Now, in pure Maxwell theory, there is no electrically charged field at all of any charge. So this endpoint doesn't exist. But in our theory, there is an electrically charged field precisely of charge QE. So maybe I want to reverse the orientation of the line in such a way that this becomes a minus sign. And when I do that, I can multiply this open Wilson line with the charged field at the same point. Now this gauge non-invariant operator is used to make the open Wilson line gauge invariant. So the combination of phi and the half infinite Wilson line is gauge invariant. And this Wilson line of charge QE can now end. Now, interestingly, right, if QE is 1 or minus 1, then every Wilson line can end because you can use powers of phi to end Wilson lines of every integer charge. But if QE is greater than 1, it means you can only end Wilson lines whose charges are commensurate with QE. So for example, if QE is 2, then the charge 1 Wilson line still can't end, but the charge 2 Wilson line can end. That's the statement that the electric flux of this Wilson line is conserved modulo QE. Okay? So now we have electric flux conservation mod QE. So a single Wilson line maybe can't end. QE Wilson lines can end in the phi field. And these discrete flux conservation symmetries are very common in physics. First of all, I mean, they occur in this model. This model is ubiquitous in physics. For example, if QE is 2, then it describes a standard BCS superconductor, and it arises in many other contexts. And discrete flux conservation symmetries also appear in non-abelian gauge theories, for example, in Yang-Mills theories. For example, in SUN, Yang-Mills theory, there's a Zn flux conservation symmetry, which has something to do with confining strings and so forth. Okay. So this model has a Ze electric one-form symmetry and a U1 magnetic one-form symmetry. Any questions? Incidentally, the mixed anomaly between the U1 symmetries in Maxwell theory, the U1 electric and the U1 magnetic, survives if QE is bigger than 1. It gets truncated to a mod ZQ anomaly, but it's still non-trivial. So one has to, in principle, match it in every phase of the abelian Higgs model one encounters. And maybe I'll say a few words about that as we go along, how that happens. I won't have time to describe it technically in detail. It will require coupling to background fields in this model, reanalyzing the gauge invariance, but it can be done explicitly. Okay, very good. So in the spirit of these lectures, I would like to understand, first of all, what are the phases of this abelian Higgs model, and to what extent can I characterize them using its higher form symmetries. So let's do what we did for the O2 model, which is to vary the mass parameter here from across the real numbers from positive to negative, and let's see what happens. All right, so let's first discuss the positive mass, the mass phase. Again, if you wish, it will be essentially correct to do this classically, but if you want to do it in a way which is kind of quantum mechanically reliable, you should look at very large masses to be in the kind of weak coupling regime. It turns out that this theory is actually weakly coupled for all values of the mass because this is an U1 gauge theory in 4 space-time dimensions, which is weakly coupled. So in fact, one can analyze this model for all values of the mass and still do reliable calculations, and I'll tell you what happens. I'm just saying, as a matter of general principle, the trivial parts of the phase diagram are always the extremely large masses. Okay. So in fact, because the analysis of this phase diagram is essentially a quantum field theory class exercise. There's a chapter in Peskin and Schroeder where they walk you through how to analyze this model. It's easy to analyze when the mass is non-zero. The point that is least easy to analyze is the massless point. So it turns out that this model has 2 phases separated by a phase transition at some point. The point is not really well defined, but you can pick conventions in which you can call it 0. This 0 is not a meaningful notion because there's no symmetry that protects the 0 mass point. So you have to, if you wish, the mass gets renormalized. This is the hierarchy problem in the Higgs model, and therefore you just have to renormalize it somehow. And I'm going to pick conventions where the transition happens at m squared equals 0, which is also where it happens classically. All right. So there's the small mass phase and the large mass phase. There are 2 phases. We'll discuss them in turn. And it turns out there's a single transition in between. Now, this model is amusing and famous for the fact that if you stare at it classically, right, the potential looks exactly the same as in the O2 model. It is the potential from the O2 model. So classically, you might think that as you go through m equals 0, the phi particle becomes massless and you get a second order transition. But there's a very famous effect that occurs in this model, which was discovered by Coleman and Weinberg in the 70s. Which is that precisely when the phi particle becomes massless, that's the only point in the phase diagram where quantum corrections are actually important. And they slightly knock the phase transition away from being second order and actually make this a first order, very weakly first order transition. So the phi particle is never massless anywhere in this phase diagram. Very good. It's called the Coleman-Weimer effect. And it occurs in many, many phase diagrams with gauge fields.
You said it's weakly first order? That didn't sound like a technical term, but is there some...
It's sort of a technical term. It's weakly first order in the sense that it's first order because of quantum corrections. And the quantum corrections involve a small in this model, the parameter E is parametrically small. It's a weak coupling problem. And so there's really a sense in which you can kind of compute the first order jump in perturbation theory, and it's very tiny. That's to distinguish it from like generic first order transition that you would encounter in some material or some lattice system, whereas you dial the parameters, you would generically encounter big gaps, big jumps. Okay, so let's first analyze the positive mass phase. The positive mass phase is the Coulomb phase of this model. So let me justify that to you. Remember that in Maxwell theory, we said that a Coulomb phase was associated with having a free photon. And that's exactly what happens in this positive mass phase. Because when the mass is positive, then the minimum of the potential is at the origin, which means that there's no Higgs mechanism. The phi particle is just a heavy particle of mass m. And if you're a low energy person who's interested in the phase of the model, the phase of the model is always a question about the very low energy physics, the very long distance physics. Symmetry breaking is always such a question. And therefore you can just forget the phi particle. If you're a classical person, you literally just erase it, and you keep the Maxwell Lagrangian. If you want to do quantum mechanics more correctly, then you integrate it out. So that means you do the path integral over phi, but not over the gauge field. And what you get at low energies is an effective Lagrangian only for the gauge field, which at leading order looks like Maxwell. And then you get corrections that involve higher powers of f. Let me schematically write them like this. So you get a power series in f and its derivatives suppressed by powers of the massive particle, the massive charged particle that you integrated out. This is an example of an effective action or an effective Lagrangian. And you can do these calculations explicitly in a series expansion in f. Okay? So you see that if you think of this derivative expansion as a Taylor series as we move home, the most important term at long distances is the term with the fewest derivatives. So that's the free Maxwell term. So as far as the deep infrared of this problem is concerned, this theory is just a free photon with a Maxwell term. And therefore, everything we said about Maxwell theory applies. There's a standard photon. The U1 magnetic symmetry is spontaneously broken. You can think of the photon as the Goldstone boson. In Maxwell theory, we said that there was also a U1 electric symmetry that's spontaneously broken. Now, here that's a little bit more interesting because in the whole model that we started with the Higgs field, this U1 electric symmetry wasn't there. It was only ZQ. But when we go back to low energies, when we go below the scale of the mass m, which is the scale at which the charged particle lives, this symmetry somehow comes back. And that's related to the fact that the charged particle is heavy, right, in this positive mass phase. So if you ask low energy questions that are not capable of exciting it, then you don't see that the U1 electric symmetry is broken. And it's what's called an emergent symmetry. It's an accidental symmetry of the low energy theory. So this theory actually has both the U1 electric symmetry and the U1 magnetic symmetry. But this one is exact, and this one is emergent. Or accidental.
Sorry, did you not just say the magnetic one is broken? Or did I?
So, okay. So you need to distinguish between spontaneous breaking and explicit breaking. Okay, so the spontaneous breaking is the statement that the current creates a Goldstone boson. So the U1 magnetic is an exact symmetry of this model. The full UV model has a closed F, therefore the U1 magnetic is there. In this phase with a photon at low energies, this F creates a photon from the vacuum. So it's spontaneously broken and the photon is a Goldstone boson. The electric one-form symmetry, that you can work out what the electric one-form symmetry is. In pure Maxwell theory, it was just star F. It turns out that in this theory, it gets corrected by higher powers of F, but the leading term at low energies is still star F. So the dominant effect at long distances is still to create one photon. So this emergent or re-emergent U1 electric one-form symmetry is also spontaneously. And the photon is also the Goldstone boson to that. Now, this is the place where I promised you at some point the fact that one-form symmetries don't act on local operators would play a role. This is the place where higher form symmetries are markedly different from normal symmetries. Because if you know examples of emergent symmetries from somewhere in physics, whether it's pion physics in QCD or whether it's condensed matter physics, you know that generally speaking, if you have an emergent symmetry and that symmetry is spontaneously broken, you don't get exactly massless Goldstone bosons. You get so-called pseudo-Goldstone bosons, which are light but not exactly massless. And that has to do with the fact that the low energy theory remembers that the symmetry was actually broken because it has operators in it that are actually charged under the symmetry. They just happen to be small. But in the case of a higher form symmetry, right, we made a very simple topological argument that there cannot be any local operators that are charged under this symmetry. And therefore, as far as this low energy Lagrangian is concerned, it's completely blind to the fact that the one-form symmetry is explicitly broken at the scale m. And the reason it's blind is because there's no term I can write in this effective Lagrangian that breaks this symmetry. To all orders in the derivative expansion in this theory, it thinks it has a one-form symmetry, and you have to kind of go beyond that. You have to start looking at non-analytic terms in correlation functions in order to see the breaking. So this photon is dead massless, even though one of the one-form symmetries is accidental. Very good. And this is a very generic phenomenon that happens in essentially all examples where you have emergent gauge theory phases and emergent higher form symmetries. So if you look at the toric code, for example, that has an emergent Z2 gauge theory somewhere, then that Z2 gauge theory at very long distances has emergent Z2 one-form symmetries, electric and magnetic. They're also broken by heavy charged matter, but they're exponentially good at long distances. So you don't see the breaking. And there's no local operators, no local deformation that can break these symmetries. So that's very important in order to stabilize these kind of gauge theory phases. Okay, very good. Any other questions about the Coulomb phase of the model? I should say that in this phase of the model, the anomaly matching, of course, works exactly as it does in free Maxwell theory, because free Maxwell theory had a mixed anomaly between U1 electric and U1 magnetic. It turns out that only the ZQ subgroup of U1 electric is exact, so only that anomaly needs to be matched, but it works exactly the same way. Okay, so now let's discuss the negative mass phase. This is what we usually call the Higgs phase. Higgs phase, Higgs phase, depending on your preference. At some point, Higgsing got turned into a verb, and that's actually the technically most precise way to say what happens in this phase. Spontaneous gauge symmetry breaking is the least precise, or maybe the most incorrect way to say what happens in this phase. Since the gauge symmetry doesn't act on anything, you can't spontaneously break it. That's actually a theorem. It's called Elitour's theorem. And it was very shocking when it was first understood. In hindsight, it's fairly obvious. Okay, so let's discuss what happens when m is negative. Just like in the O2 model, the potential now has this shape, this famous shape with a degenerate circle of minima, right? So it's like taking the Ising symmetry breaking potential and revolving it around its symmetry axis. So this is the complex phi plane. And in the O2 model, we had an entire circle of minima, and each of these minima was physical and observable, and the two different points on the circle were not the same vacuum. They were different vacua, and then there was a symmetry that was relating them. Here, the gauge transformation, the gauge redundancy of this model allows you to completely kill the phase degree of freedom in phi. If you wish, you can fix a gauge in which phi doesn't have any phases. That's what's usually called unitary gauge. And what this means is that you should forget about the angular direction of this model. Okay? The angular direction is no longer a physical degree of freedom. It just disappears. And therefore, we really only have this kind of radial direction, and we only have a single one Higgs vacuum. In this Higgs vacuum, phi gets a non-zero expectation value. And if you wish, you could, based on what I just said about the phases, you can make this real and positive. And in this Higgs vacuum, there are no massless particles whatsoever. In the O2 model, there was a massless Goldstone boson associated with the presence of the angular direction, but the angular direction here is gone, and so is the Goldstone boson. We only have two massless particles. We have the so-called Higgs field, which is the thing corresponding to the radial oscillations of phi. That has some mass because the potential is convex up. And then the photon acquires a mass because phi gets a Bev, right? If phi gets a Bev, if phi has a constant expectation value, then expanding out this kinetic term gives famously a term that looks like a squared mod phi squared. And when phi is non-zero, then this is a mass term for A. So the photon is now a massive spin 1 particle. So we have a massive spin 0 Higgs particle and a massive spin 1 photon A. You can compute the masses in terms of the Bev, lambda, and E squared, and you'll see that everything is massive. Mary?
Can I ask?
Yeah.
The statement that phi gets a Bev makes sense only once we gauge fix, because it's not a gauge invariant operator.
Well, that's not quite true. The fact, so the gauge transformations can only change the phase of phi, so the fact that it is non-zero, that it is a gauge invariant statement. Its precise value is not gauge invariant, but its magnitude is gauge invariant. So we can definitively say that it is non-zero if its magnitude is non-zero. Very good. All right, let me continue on the left side of this board. Now, what happens to, how are the symmetries realized in this phase? Well, we had a U1 magnetic symmetry, which was continuous with current F, and then we had a discrete ZQ symmetry, which we'll get to in a second. So let's first ask whether or not this symmetry, this continuous U1 magnetic symmetry, is or is not spontaneously broken. Well, remember, what was the trick, or the fast way to check that a continuous symmetry is spontaneously broken? The trick we used in the Coulomb phase, try to act with its current, with F on the vacuum, and you ask whether or not you get a massless particle. So you act with F on the vacuum, and you ask what you get. Well, F is the photon field, and acting with it on the vacuum creates one photon. That's still true, but now the photon is massive. So this only creates a massive particle. There are no massless particles in this model. And therefore, there's no Goldstone boson for this U1 magnetic symmetry. So therefore, the U1 magnetic symmetry is unbroken. Higgs phase is distinct from the Coulomb phase through the way that it realizes the magnetic one-form symmetry. And you can, of course, distinguish these two phases because one of them has a massless particle and the other one doesn't. But now you can reinterpret that observation in terms of symmetry breaking. The same way that you interpret the broken and the unbroken phase of the O2 model in terms of standard symmetry breaking of a U1 zero-form symmetry. Very good. Now let's think about what happens to the ZQM one-form symmetry, this discrete one-form symmetry. Of course, if QM is 1, then this symmetry is trivial, and the Higgs field has charge 1, so it in fact completely Higgses the entire gauge group, and since there is no more one-form symmetry, there's no anomaly, because this was a mixed anomaly, and so there's nothing to match. So the case QM equals to 1 is trivial. But the case QE bigger than 1 is interesting. It would be like 2 and 1. And the reason it's interesting is because the presence of this mixed anomaly between ZQE and U1M means that the low energy theory, despite being gapped, despite not having any massless particles, cannot be empty, cannot be trivial, right? So there has to be some kind of dynamical system, quantum field theory system at low energies that is capable of matching this anomaly. And that is a topological field theory that arises from the fact that if QE is not 1, the charge QE Higgs field cannot completely Higgs the entire U1 gauge group. It can only Higgs it down to its ZQE subgroup. So U1 gauge group is Higgsed to its ZQE subgroup. In this equation, I'm not writing one-form symmetries, I'm writing gauge groups, something I've mostly avoided. This is the U1 gauge group of the model. And when phi gets a VEV, the stabilizer group of phi is the ZQE subgroup of U1, because phi has charge QE. So ZQE subgroup of the U1 doesn't get Higgs, and that means that if you are very careful, then you detect at long distances a ZQE discrete gauge theory. So this model has topological order. That's true even of a standard BCS superconductor. I told you that for charge 2, this is the theory of a BCS superconductor. BCS superconductors are topologically ordered at low energies. And this ZQE gauge theory is in fact capable of matching this anomaly. Might not have time to say a lot of details about that, but maybe I can get started in the right direction. Before I tell you a little bit more about the anomaly, let me tell you about kind of the physical way or the physical reason that the anomaly is matched, and it has something to do with the things that are charged under the U1 magnetic symmetry. Now, we concluded that in the Higgs phase, the U1 magnetic symmetry is unbroken, right? That there's no Goldstone-Boson. That's nice. We concluded that just based on looking at what the current is. But remember from yesterday that one of the important things that you get to ask when there's a symmetry and it's not spontaneously broken in the vacuum is you get to ask what representations of this symmetry does the Hilbert space contain? Or in other words, are there charged things, charged particles, charged excitations of some kind that actually carry this unbroken symmetry? You cannot ask that if the symmetry is broken, because then, the Hilbert space doesn't break up into representations. But since the symmetry is unbroken in this phase, you can ask what kind of sectors of the Hilbert space are charged under it. And well, whatever they are, they have to carry magnetic flux, right? Because this U1 magnetic symmetry measures magnetic flux. So it turns out that the things that carry magnetic flux in this Higgs phase are the famous magnetic or vortex strings. Sometimes they're called Abrikosov-Nielsen-Olsen vortices. They also occur in superconductors. They also occur in this version of the model. So these are topological defects that are essentially dynamical magnetic flux tubes. You see, the thing that carries magnetic flux was the 't Hooft line. That was the thing that was charged under magnetic flux. If you act with that on the vacuum, you create something that creates magnetic flux, but it has to be living on a line because the 't Hooft line is a line. So the things that carry magnetic flux are strings, one-dimensional objects, and you all know what the solenoid is, right? That's exactly what this string is. It's a solenoid that carries in its interior magnetic field. But in this case, the magnetic field is not something that you somehow put in by, you know.
Sorry, there's a group of dummy mathematicians who have no idea what a solid is.
Solenoid is a cylinder with a magnetic field in it. So this is a fairly accurate description, depiction of a solenoid. Right. So the only difference is that, you know, in the cylinder is not rigid. It's not some kind of external vessel in which you put a magnetic field. In this case, this solenoid is an actual dynamical excitation of the field theory. In other words, it's like a particle, but it's extended along one dimension. Right? A particle is a dynamical excitation that you create when you act with a field on the vacuum. This is a dynamical excitation that you create when you act with a line operator on the vacuum. And it's charged under this U1 magnetic symmetry. That's true even if Q electric is 1, right? These magnetic vortices always exist. Very good. So this is a sort of, yeah, okay, I don't want to say too much about that. Now, when the low energy theory is trivial, these vortices all carry magnetic flux, which is an integer, because they are created by nice 't Hooft lines which carry integer magnetic flux. But it turns out that when there is this phenomenon that QE is positive and you have a topological field theory at low energies, then you can also find vortex excitations that carry fractional magnetic flux. And in fact, you can find fractional vortices that are precisely quantized in units of 1/2e. And the fact that the vortices can, and you can do this totally explicitly, by the way. I mean, these vortices are solutions of the field equations of this model, which can be analyzed explicitly, and you can find vortex solutions for all of these charges. And if QE is not 1, then you can find fractionally charged vortices. So this is an interesting baby example of something very general that occurs all over the place in field theory and other systems, which is something that people now usually call symmetry fractionalization. So you have a U1 magnetic symmetry here, which is ostensibly such that all things that are charged under it should have integer charges. But sometimes you find that in special circumstances, some things can carry fractional charges. And there's always a good reason for that I won't have sort of time to spell out in general. But in this case, the good reason is that these fractionally charged vortices are precisely what ends up matching the mixed anomaly between this ZQ electric one-form symmetry and U1 magnetic symmetry. So the fact that the vortex charges are precisely quantized in units of 1/QE is what's needed to match this ZQE mixed anomaly with U1. Okay, so I think I'm slowly running out of time, so maybe I will not explain that in detail. So maybe I'll just summarize a little bit what we did here and then say a few more things about what lies further down the path that we could have continued walking on. So we've seen at least one non-trivial, non-free model that's physically interesting. That's a gauge theory that has different phases. And we see that we can understand a number of different things about these phases using the higher form symmetries of these models. Some of these are restatements of well-known things. Some of them, like the matching of this anomaly, is sort of new and subtle and wasn't necessarily understood in this way before. So now one can go ahead and sort of try to apply these methods to more and more interesting theories, in particular non-abelian gauge theories, where one is interested in things like confinement and QCD. Maybe the only thing I would want to say about confinement is that in our modern understanding of what confinement should look like, it's actually indirectly very closely related to what happens in this abelian Higgs model. Because the abelian Higgs model has these strings in it, and if you measure the amount of work that it takes to separate the end of the string, then the tension of the string will pull back against you. Now, because the string carries magnetic flux, if you actually end it, right? Remember that if you end something that carries electric flux, it needs to carry electric charge. If you end a magnetic object, it has to carry magnetic charge. So these strings have magnetically charged particles at their endpoints. And so the fact that the strings have tension is tantamount to the statement that it's impossible to separate the magnetically charged objects from each other in a Higgs phase. That's essentially the Meissner effect in superconductors in physics terms. So it's the fact that you can't have isolated magnetic charges in a Higgs phase. Now, if you simply reversed the words electric and magnetic in this story, and you think about the electric-magnetic duality of the free Maxwell theory, which is not really a symmetry of this model, but if you just simply sort of go with the flow and exchange electric and magnetic, then you would end up with a picture where instead of a magnetic flux tube, you would have an electric flux tube, and instead of magnetic charge at the ends, you would have electric charge at the ends. And you would learn that separating these electric charges because of the tension of the flux tube would cost you more and more energy as you pull them further apart. And this is precisely the way in which we understand confinement in Yang-Mills theories and in QCD. So roughly speaking, it was already understood in the 70s at the level of cartoons that confinement should be some kind of electric-magnetic dual of what happens in this model. But to actually make that precise took much longer. It can be made precise in some supersymmetric theories, and to make it precise in real Yang-Mills theory and real QCD is an open problem. So, anyway, maybe I'll stop here. Any questions?
Are there examples such that you have some one-form symmetry as an immersion symmetry, but somehow the effective Lagrangian has some explicit symmetry breaking term, but they are irrelevant?
No, I told you that there are no local operators whatsoever that are charged under the symmetry. It doesn't matter whether they're irrelevant or not. It doesn't matter how irrelevant, there is no local operator that can break a one-form symmetry. That might incorrectly lead you to believe that the one-form symmetry is actually exact. But that's not true. These low-energy effective actions, you should think of them as a series expansion.
Because they have infinite.
It's a Taylor expansion of a physical observable, like a correlation function or something like that, which to all orders on the perturbation expansion, to all orders in the Taylor expansion, has the one-form symmetry. But then there are non-analytic terms that are very small, that have zero Taylor expansion to all orders, but that break the one-form symmetry.
More physical question. You said that for Q equal 2, you have a description of a superconductor.
Yeah.
But if I remember correctly, there should be a second order phase transition for a superconductor. This is first order. It should be. Either I remember wrong, or maybe the.
No, you're remembering the wrong dimension.
Okay.
This is a superconductor in, well, depending on, if you're doing classical physics, it's a superconductor in 4 spatial dimensions. So the physically interesting case is in 1 lower dimension, where the physics of the model is much more interesting. Then, indeed, there's the possibility of having either a first or a second order transition, depending on the ratio of parameters in the model. But in 4 dimensions, 4 space-time dimensions, or 4 Euclidean dimensions, this doesn't happen.
No, I was just thinking, there's also, you could have other transitions, right? That, for example, from like a Q equals 1 to Q equals 2, like from a trivial phase to this Higgs phase. Or rather from the trivial Higgs phase to this Higgs phase with the unbroken Z2 symmetry.
Well, not in this model.
No, not, but
need to add more
wouldn't
fields.
that be second order?
No. Why? Why do you think so? Well, first of all, you would have to tell me what the model is before we can discuss what it does. You would certainly have to add more fields.
Yeah. I guess the second Higgs field, right?
Yeah, you'd have to add a second Higgs field, maybe of charge 1.
Yeah.
You could do that. That by itself would not make the transition second order. I think if you add like 20 Higgs fields, maybe. There's some critical number of stuff you have to add to make it second order. Other questions? Well, I guess we can transition first or second orderly into the Q&A. Thanks.